Hello, today I will be demonstrating my understanding of simple linear regression, multiple linear regression, and polynomial linear regression through my completion of the early test. So in exercise one, we were given a data set that included a study of different factors associated with prostate cancer. We analyzed the data through scatter plots and a correlation matrix. And as you can see in the correlation matrix, there are already a few factors that are moderately correlated with each other, which already raises some initial concerns for multicollinearity. So we build the appropriate MLR model, and we can see that although the overall model is significant due to the very small p-value and very large f statistic, we can see that not every single factor is significant, which shows that there are even greater concerns for multicollinearity. The adjusted R squared value, which we use because it takes into account the degrees of freedom, it's okay as it is 0.58. However, it could be better, which means that this MLR model may not be exactly the best fit model for the data. So to further explore the concerns with multicollinearity, we can calculate the variance inflation factor values for each of them. And the VIF value should ideally be as close to 1 as possible, which, as we can see for each of the factors, this is the case. They are all fairly very close to 1, which means that multicollinearity isn't a great issue in this model. We can go up and look at the residual analysis, and if we take a closer look at the residual versus fitted plot, we can see that there is a potential pattern going on with the residuals, which means that we may not be able to assume linearity. In addition, in the QQ residuals plot, we can see a slight deviation from normality right here, which means we may not be able to assume normality of errors. Further analysis is needed to explore the extent of the deviation from normality and the pattern within the residual versus fitted plot. If I were to build a parsimonious model through criterion such as AIC and BIC, I would retain the predictors L caval and L weight due to their very small p-values and due to their relatively ideal VIF values. Now on to exercise 2. We had to analyze data from a study of bacterial growth in a bacterial colony over time. And as we can see in the plot of time versus size, we can see that it is suggested that a linear model may not be the best fit for this data as there's a clear curve in the plot. But anyways, we still fit the data on an SLR model. And despite the p-value being fairly small, the adjusted R squared value being fairly large, and even the residual standard error value being fairly small, we can see how crucial it is to check our model assumptions through residual analysis. As we can see through the residuals versus fitted plot, there is a clear, smooth curve here, which means we cannot assume linearity nor independence. In addition, there is a slight but noticeable deviation from normality in the QQ residuals plot, which means that we may not be able to assume normality of errors. So, in order to capture the biological fact that bacteria actually grows better in the dark compared to the day, we need to use a UPR model through the interaction of time with itself. And looking at the UPR model, the p-value is even smaller, the adjusted R-squared value gets larger, and the residual center error value gets even smaller. And if we look at the residuals plot, there is random scatter, there is no clear pattern, so we can assume independence and linearity. And with the QQ residuals plot, there is no noticeable deviation from normality here, so we can assume the normality of errors. There are, however, a few aspects that we do lose as a result of using this UPR model. The first being we will not actually know now the true extent to how time affects the growth of the bacterial colony due to the interaction of time itself. In addition, if we extrapolate beyond the initial data, we may not actually know the appropriate direction of the predicted response.